Hello and welcome back to our tutorial sessions on how to use MATLAB for various calculations on transmission lines. The section that we will talk about today is on how to use MATLAB for matching impedances, and we will consider two specific examples. The first is when you have a quarter wave transformer that is coupled with a complex load. So this diagram over here shows a complex load which has a resistive and a reactive component connected with some length L of transmission line to a quarter wave transformer. We know that having real loads on either side of the quarter wave transformer is good because it gives us a real value for the characteristic impedance of the quarter wave transformer, and that's important to so as to not have any power lost within the matching network itself. So how do we design this length of transmission line L? Previously, people have used Smith charts. In today's tutorial, you'll see how do we do this with a MATLAB function. Okay. The second aspect that we will look at is stub matching, and we'll get to this when we finish the section on quarter wave transformer. Okay. So let's start our MATLAB code over here. So let's give it a heading. So this is MATLAB code for impedance matching on transmission lines. Okay, right. So I've already done this before, but I'll do it once more. So clear the workspace and the command window so that it's we have a clean slate to begin with. Let's assume some value for the characteristic impedance. So let's say Z0 is equal to 50. And this is the characteristic impedance. Okay, and just for sake of argument, let us take a complex load. Let's call it, we can take any value we want. Just for simplicity, I'm going to take 75 plus 1j 100. Okay, so this is the load impedance which is connected with some length L. All right. Okay, so let's have a look at our circuit diagram again. So this is the circuit diagram picture that I have. This is the ZL whose value I've given as 75 plus 100j, and I need to calculate what is the length L such that after the transformation the transformed impedance, which is given by this formula over here, becomes purely real. Okay, so I need in a sense a function which calculates this impedance transformation. Alright, so let's think about how we can write this. Okay, so let's write this over here. So impedance transformation. Now in previous tutorials we've seen how we can write functions as standalone files. In this example, what we'll do is we will include this function as part of the main script itself, just for reasons of compactness, nothing else. Let's also give our code a name. So let's call this transmission line impedance matching. So the impedance transformation function is what we need to write down. Okay, so how do we do this? The syntax is exactly similar to how we had written a function, for example, over here previously. So the function output parameters equals to name of the function and the input parameters. So I want this function to return to me the transformed impedance. So I'll say ZL transformed. Okay, that's the output, and let's say impedance transform. And what should be an input to this function? Of course, I need to give it Z0, I need to give it ZL, and also I need to give it the length of transmission line L, which I want to transform it by. Okay, so let's write this and give it a brief comment over here. Transform the impedance by length L. Okay, let's write an end over here so that the function syntax is complete. Okay, now what we need to write down now is basically implement the formula. So if you have a look at this formula again, you can see it over here at the bottom, Z0, ZL plus J, Z0 tan beta L. Now we can straight away write this as ZL underscore T. That's the answer that I want. I can write this as Z0. Okay, and look at the formula again. So it's ZL plus Z0 tan of, now you notice I need beta as well. It's not enough for me to just have L. So I need to make sure that I have given it as input to the function. So I make sure that beta is in the input. So tan betas L, okay, and I will divide this by Z0 plus ZL tan beta L. I have forgotten the J term over here, so 1J. Similarly, there is a 1J term over here. This is right. So this is the formula that we had. You can just confirm it's exactly what we had over here. Now this is the way that we wrote the formula in the PDF, but when we go to evaluate this numerically, there is going to be a problem, and that problem will specifically arise when beta L is pi by 2, because under those circumstances what will happen is tan of beta L will tend to infinity, and in any programming language it's not a good idea to have infinity or very large numbers, nans floating around. So this might seem like the natural way to write it based on a formula that you see in the book, but in terms of implementation this is a bad idea. All right, so what we'll do is we'll just comment this line out because we don't want this implemented. Let's write down the formula in terms of something that will not give me infinities, and that is if I write it in terms of sine and cos instead. So Z0, okay, so this is the common term, and so what happens is pretty straightforward. I will have a cos beta L, okay, plus 1J Z0 sine beta L. Now notice that this function, the length of this function is sort of becoming quite large, and it for readability it's better for me to give a line break over here. So a very simple way in MATLAB to continue on to the next line is to put down 3 dots. So I give it a space, 1, 2, 3 dots, and enter. So it's going to continue this function on the next line. So I need to give a divide. All right, and let's say let's put down the rest of the syntax. Cos beta L plus 1J ZL sine beta L. Okay, so the function looks almost ready. Except for one small problem, is that supposing I want to calculate this impedance transformation at various different values of length L. Alright, so this function is fine, there's nothing wrong with it. But now imagine instead of calling this function with scalar values of Z0, ZL, beta and L, I call it with an array of different possible values of length L, and for all those different possible values of length L, I want to find out what is the transformed impedance. So what would happen is that this numerator term over here would become an array, because for every different value of L I have a different value of numerator, and have similarly the denominator has also become an array for different values of L. And when MATLAB tries to divide two arrays of incompatible sizes, I can't divide a 1 cross n matrix by a 1 cross n matrix. What I actually want is element wise division, so I put a dot over here. This completes my impedance transformation. Okay, so in this problem, therefore I should also specify the wavelength so that I can get beta. For simplicity, I'm going to say that the wavelength is simply 1 meters. Okay, so this is wavelength in meters, and from that I can define my beta is 2 pi by lambda. Okay, so this is the function is sort of ready. Now let's just give it a test. So for example, let's say that L is equal to, let's say, lambda by 2. Okay, and let's call our function. So let's say ZL underscore transformation is impedance, right? So let's give it Z0 ZL beta L, right? And now let's just run our function to see if everything is all right, right? So what do we get? The answer is seen over here. So it's 75 plus 100J, which makes perfect sense because I have done a transformation by lambda by 2. We know that on a transmission line, the impedance stays the same if I do a transformation in integer multiples of lambda by 2. So this just confirms that everything is all right with the coding of our function. Okay, so this is just a test. So let's write down test and let's comment this out. Okay. Now is the part for which traditionally we have used Smith charts. I want to find out that L for which there is a real part of the transformation. The transformation becomes real. So the first way in which we would want to do this is just to visualize what does this impedance look like when for different values of L. So as we have done before, let's create an array. Now L will no longer be a scalar. Let's make L into a array. So let's say L. I want to examine how this impedance looks like, and I go from 0 to lambda by 2, because I know that it will repeat after lambda by 2. I need not go in excess of lambda by 2, and I want a very fine spacing just so that it's easy for me to visualize this. So let's make it lambda by, let's say, 100. Why not, right? So it's going to create an array of let's just run it once and see what is the size. If I run it here, so L is an array of size 1 cross 51, which has all these different values in it, and for this I want to calculate what is the transformed impedance. So let's say ZL underscore T. I can use the very compact MATLAB notation. I can just give the function, and as input is the entire array, okay, and I should remember to terminate this with a semicolon, otherwise I will see a huge output, okay. And when I run this, what will happen is that I'm going to get ZL underscore T will become a complex array. So just to confirm, let's run it once. There you go, ZL underscore T has become an array. Now I want to look at the real part and the imaginary part. So let's do that. So let's use the plotting facility which we are familiar with. So let's create a new figure. That's the command to make a new figure window. And I want to plot the real part and the imaginary part in the same window just for convenience. So I'm going to use a new command which is subplot. I want to create a 1 by 2 sort of array of plots, and I want to first specify the left hand side. So 1, 2 tells me the size of the plot window, and this tells me the current plot which I am going to specify, okay. And now I say plot. What I want is L is the x-axis, and I want to plot the real part of ZL underscore T, okay, and let's say plot it in red, okay. And I always like to have a grid for it. X label is going to be L, right, and let's give it a title, real part, right, and let's specify the second part of the plot, which is 1, 2, 2, okay, and this time I want to plot the imaginary part of ZL underscore T, and let's give it a blue color just to make it clear. X label is L, and the title is the imaginary part, okay. The Y label is fixed to be ohms. I need not specify that right now. Let's go ahead and run this and see what we get. There you are. So you notice the real part is sort of starting from the real part is starting from 75, which is what we expected, and it's ending at 75, which is exactly what we expected. The imaginary part starts out at, when it comes, you can see the tooltip will give me a value of 100 over here, and it ends at 100. Okay, so that makes perfect sense. X is equal to 0.5, that's the length L that I have specified. Lambda is 1. Right. So what are we looking for? We are looking for that value of L for which the imaginary part, so here is the real part and imaginary part, so the imaginary part should go to 0. So I know that there seem to be two possible solutions to this equation. Now solving these set of equations analytically, you are dealing with, for example, if I wanted to solve the problem of finding out the point where the imaginary part went to 0, then I'm solving transcendental equations, and it's time consuming to solve it with pen, paper and calculator. So which is why Smith charts have been used. Now what we'll do is we'll try to use a inbuilt function which finds the zeros of a function. Okay, so let's get started. Right. So this is done, the plotting is done. So let's use a function called f0. All right, so let's just type in help f0. Okay, so f0 is, let's make it this bigger. So what does f0 do? right? So it's a single variable nonlinear zero finding. So it tries to, so for example, it says here f0 of a function and given x0, it tries to find a zero of the function near x0 if x0 is a scalar, and if x0 is a vector of length 2, right, it assumes that it is that I am looking for a zero in a finite interval where the function changes sign and therefore a zero must have occurred, right? An error occurs if this is not true, meaning if the sign of the function does not change between f function evaluated at the left side and the right side. Anyway, we need not worry about this too much. We've got the basic syntax is to call this function f0 with our own inbuilt function which will do the impedance transformation. Now notice that our function, the function that we have written over here, it does not return a single function, right? It does not return a single value. It returns two values, the real part and the imaginary part. So when if I try to give this function impedance underscore transformation as an input to f0, it will complain because it does not know which to make a zero out of, the real part or the imaginary part. So instead of rewriting another function which will just send the real part, what I'll do is let me create what is an anonymous function which we have seen before. So let's do impedance matching for zero imaginary part, right? So it's the imaginary part I'm interested in. So let's create a new function. Let's give it a name. So impedance underscore imaginary part, right? This is going to be a function of only one variable. Okay, remember this has to be a function of function. So for example, in the documentation, accepts real scalar input x. This function over here, impedance underscore transformation, does not take a scalar input. It takes a vector input of 1, 2, 3, 4 values, right? So that's one more reason why I need to define my own function. So let's define the variable. So it's going to be L, and what is the output of this? So output is going to be impedance underscore transformation and z0, zl, beta L, right? So the first three arguments are going to be common, and L is what this new function which I have created, impedance underscore imaginary, is only going to return the imaginary part of the transformed impedance, and all it needs a single argument as input, which is the length L. Okay. Now with this, so now we are ready to use our f0 function. All right. So let's just try it out without any input, right? So let's see what happens. So let's give it a length L, capital L is equal to f0, and let's just give it, right? It's not necessary to find out, it's not necessary to specify x0. Let's run our function and see what happens. Right? To prevent multiple figure windows from opening up, let's close all and let's clear all. Right? So this is the start. Now let's run it. Okay, so this is our plot as before. Oh, so looks like I was wrong. It needs at least two input arguments. Okay, so let's give it an input argument. So let's say 0. Okay, find me the nearest zero crossing near L is equal to 0. So I go ahead and hit run, right? So here is what it has told me. It has told me at the value of 0.0518, right? Let's make this bigger. If I take it over here, right, it's roughly somewhere over here, and that's exactly what the output has told me. 0.0518 is where the first 0 has happened over here. Okay, so that's actually the length that I'm interested in, and what we could do is, so this is giving me the closest zero crossing to 0. Now let's say I wanted to find out this length L over here, the second length L where the impedance became purely real, right? So I can see that it's between 0.2 and 0.4. All right, so let me give that as an output, as an input. So L is equal to f0, so 0.2 to 0.4. Okay, and let's keep both the outputs so that we can appreciate what's happening, and let's hit run over here. right? So you can see the output is the first zero crossing happened near 0.5, which is what we expected. The next zero crossing happened near 0.3. Now what I can easily do from here is I can plot, I mean not plot, but I can output what is the value of the real part which is needed in designing the quarter wave transformer. So what I can say over here is I need to call the impedance transformation with this formula once again. So impedance underscore transformation Z0 ZL beta and now capital L. This will send me the value of the complete impedance transformation, right? Similarly, I can do the same thing over here, right? And let's hit run over here. So it's going to give me two outputs. Let's move this a little bit here, right? So the first, for the first value over here, which is 0.05, you notice that the answer given is 230 ohms, and you can notice there is a non-zero imaginary part, but it's very small, negligibly small, 10 to the power minus 14, so we can count that as numerical error and forget about it, right? So this is basically 230 ohms is what we have got, all right? And the next answer is that we have got is 10.8 ohms. So there is a choice which the user has. Remember that these values are going to repeat every lambda by 2. Now, so once I know these two values, I can keep adding integer multiples of lambda by 2 to get what are the possible values of length for which the impedance is purely real, and those purely real values are going to be either 230 ohms or 10.8 ohms. Okay, so this is how we would do impedance transformations in the case of the quarter wave transformer, which needs to see a purely real resistance at this side.